Now we get to talk about a specific type of probability distribution. We're going to focus on binomial probability distributions with this lesson. So first, let's explain what this type of distribution is. First of all, so I'm going to go down to these things first. For a problem to qualify as a binomial experiment, you have to have a fixed number of trials, okay? There can only be two possible outcomes. You either succeed or you don't, okay? Hence binomial, that word, right? So our binomial probability distributions, there's only two possible outcomes, and then there is a fixed probability attached to each of those outcomes, and they remain the same for every trial. Okay. Another condition is the trials do need to be independent and they're repeated identically. All right. So here's an example. We flip a coin 3 times. Okay. So we have 3 trials. The experiment is flipping a coin. There are only 2 outcomes, right? We have heads or tails. So that fits. And there is this probabilities remain the same for getting a head or getting a tail for each of those flips. That makes sense? So this is a binomial probability distribution. So if I wanted to find the probability of getting exactly 1 head in those 3 flips, one way to do this is to actually write out each of the specific ways I could get 1 head, right? Either the first flip could be heads, or the second flip could be heads, or the third flip could be heads. And I can find the probability of each of those, right? Just using our counting rule that we learned in a previous lesson. The probability of getting a head on the first flip is 1/2. Probability of getting a tail on the second flip is 1/2, and a tail on the third flip is 1/2. So 0.125 is the probability of this first outcome. 0.125 is also the probability of the second outcome. And same thing for the third one. So my combined probability for getting exactly 1 head would be the sum of all of those individual cases. Okay, so I have a 0.375 probability of getting exactly 1 head. All right, so there's an example. There's a probability distribution involved. We could make a list of the possible outcomes and the probabilities attached to each of them, right? All right, so let's tie this into another example to make this hit home. So we have a professor that has a 4-question multiple choice quiz. Each of the questions have 5 possible answers, and only one of those answers is right. So Eric opts not to study at all. He's just going to guess randomly on each of these questions. So we want to find the probability that Eric guesses exactly 2 questions correctly. Got it? All right, so let's piece together what we know from this problem. First, let's identify what a success is. So a success, Eric guesses the question correctly, right? The failure is that he guesses incorrectly on a question and gets the question wrong. So it's good, always good to identify what the success and what the failure is in any of these problems. So by the way, we're talking about qualitative data here, right? Whether you get something right or wrong, whether you get a head or a tail. It's qualitative data. So that's typically associated with these. Okay, so now we're going to find the probability of Eric guessing a question correctly. So if there's 5 responses, one of them is right, what's his probability of guessing that question correctly? 1 out of 5, right? So that is the P here. So note here, the P represents the probability of success. He has a 1 in 5 chance of guessing right. So Q represents the probability of guessing incorrect, right? Of getting the problem wrong, of failing the trial. And so he has a 4 out of 5 chance of failing, of not getting it right. N represents the number of trials. So how many trials are there in this multiple choice quiz? There's 4. Each question is an independent trial, okay? So N is 4. The X represents the number of successes that we're interested in. So we want to see the probability of Eric guessing exactly 2 of these questions correctly. So the X is 2. Make sense how we got all those numbers? Now we've explained it here, what each of those pieces represent. So you can use that as a reference. And so now we're going to put these together to find this probability. Well, we'll do it, of course, the hard way first. Okay, so on B, let's list all of the possible ways that Eric could get 2 questions correct. Well, he could get the first 2 questions right, successes on those, but fails to get the next 2 questions right. That's one possible scenario. He could get the first and the third question right. Right? He could get the first and the fourth question right. Oh, or he could not get the first question right, but he gets the next 2 right. Nice. Or he misses the first question and he gets the second and the third question right. Okay. Or he misses both the first 2 questions and gets the last 2 questions right. Okay, so we have 6 scenarios here where Eric could actually guess exactly 2 questions correctly. All right. Fair enough. So that means there's 6. Now, there's a shortcut to that. Okay, we did all this work with combinations before. So to get the number of total ways that Eric could get 2 questions right, we could do combinations of 4 things, and he's choosing 2 of them. No, that is equal to 6. That makes sense, right? So that expression will come up a little bit later, so you don't have to make an exhaustive list of all the possible ways that Eric can get that many questions right, okay? So in this instance, we could find the probability of each of these 6 outcomes, okay? So a 0.2 chance of getting the first one correct, 0.2 chance of getting the second question right, a 0.8 chance of getting the third one incorrect, a 0.8 chance of getting the fourth one incorrect, and we can multiply those together. By the way, these fractions, those are 0.2 and 0.8, so that's where those numbers are coming from, okay? And so essentially, you'll still, for all of these other 6 or the other 5 ways, you still have those same numbers being multiplied together, right? 0.2 times 0.8 times 0.2 times 0.8. It's still going to give you the same results. So for each of these 6 possibilities, there will be a probability attached to that particular outcome of 0.0256. Well, so there's 6 of those. So we add all 6 of those together, or do 6 times the 0.0256, and our total probability of Eric guessing exactly 2 questions right is 0.1536. Well, I told you that little hint about the combination, so we can simplify this and come up with a pattern. So essentially, this formula right here does what we just did. Okay, so we do the combinations of n things, we're choosing x of them, times the probability of success to the power of how many successes we expect, times the probability of failure times the power of how many failures we'd expect. Okay, so in our case, we had 4 choose 2, okay, combinations. That gave us the 6. We expect 2 successes, and we expect all the rest of the trials we expect to be failures. That's our 4 minus 2, so that'll actually be 2 failures as well. All right, so that formula is pretty slick. Note that down, know what it means. There on your, so let's go, and I'm going to do another scenario just to make sure we have a handle on this. What if we wanted to find the probability of Eric guessing exactly 3 questions right? How would this formula change? Okay, well, we still have 4 trials, but now we want to see if Eric, the probability of Eric getting 3 of them right. So our X is now 3. So now our probability of success, 0.02, is raised to what power? How many successes do we want? We want 3 of them. And then our probability of failure is raised to what power? Well, 4 minus 3. Okay, that'll be everything else. So we expect, if we expect 3 successes, we'll have 1 failure, right? And now we can compute that. No, you could punch in that formula with your calculator's help. We taught you how to do combinations on there, right? So go to the math and probability menu for NCR. Choose 3 times 0.2 raised to the power of 3. Right, hit the right arrow to get out of the exponent, right? And then times 0.8 just to the power of 1. Enter. So we have a 0.0256 chance of getting 3 right. So a 2.56% chance that he'll guess that many right. So not very high. Okay. So hopefully Eric learns from this and chooses to study next time. Random guessing isn't going to be to his advantage. Does that make sense? All right, so here, boom, 0.0256. All right, so now, new scenario. Let's say we want to see what Eric's chances of just passing this exam are. Okay, so, and this is a pretty liberal view of passing. Let's say that passing is getting 2, 3, or 4 of these questions correct. All right, so he only misses 1. Fair enough. All right, so we, option number 1, we could do this, apply this formula, the binomial probability formula, for each of these numbers of successes. So we just did 4. I just showed you if he gets 3 right, that's 4 choose 3 times 0.2 to the 3rd power times 0.8 to the 1st power, right? Or 4, now we have 4 choose 4 times 0.2 to the 4th power, and then what's my power for the, what's my power for this failures? Well, I succeed with everything. That means I don't fail at all, right? So that power is 0. So we can write those expressions. We can compute those all by hand, right? So we've done those first couple. So for our first one, it was 0.1536 was the decimal that we ended up with, 0.1536. For our second one, we ended up with 0.0256. 0.0256. So now for the third one, we'll go here and let's do, I'm just going to take this same expression, You can type it all in if you want. We're going to do 4, choose 4 for the first one. Our power for the successes is now 4. Our power for the failures is now 0. Boom. That gives us 0.0016. Okay, so now we add all of those up and we'll get the probability that Eric gets 2, 3, or 4 right, because that's an addition rule problem. Okay, we talked about those probability type problems. Okay, it's an or case, 2, 3, or 4. So we add them up, and what do we get? 0.1536 plus 0.0256 plus 0.0016. And we end up with a probability of success of 0.1808. So an 18% chance that Eric will pass just by randomly guessing. Okay, still not that great. He has a much better chance of studying. So there we have it. So there's our answer to C. Boom. And then convert it to a percent. We have an 18.08% chance that Eric gets this right. And now let me show you another way. So note those first ways of doing this, I just used that entire formula with the NCR thing, right? The binomial probability formula, that's great, but that's a lot of key presses. There is another option on our calculators, and that's going to get us into our distribution options in our calculator. So we're going to hit second and variables, and this gives us a list of distributions. We'll use several of these throughout the rest of the class, but we're going to hit the down arrow for now and go down to our binomial PDF. A binomial probability density function is what that stands for. And press enter. And this binomial PDF is going to require N, P, and R. The number of trials, the probability of success, and the number of successes that we are interested in. So for that first one, first case, the probability of getting exactly 2 questions right, we have 4 trials. The probability of success was 0.2, and our X, the number of successes we were interested in, was simply 2. So TI-83 people, you're just going to see this command line version, and so you just have to remember that those are the options that you put in a comma separated list inside those parentheses. N, comma, P, comma, R. Okay, TI-83 people, you just have to remember that, okay? And press enter, and that gives us that particular probability. A lot easier to type than doing the actual formula, binomial probability formula every time, right? And then we can just reuse this. Number 3 successes, oh, that's just what I got before. And 4 successes, look at that. That's what I got before. So pretty slick. Okay, so now some additional shortcuts for this. Let's say I want to do binomial PDF, but for that third option, so let's go all the way down here again. We'll go through the entire steps. Boom. For that third option, instead of putting in a number, let's clear that out. Let's put in the list of numbers. So now those curly braces, I don't know if you've noticed where those are at. I believe it's second and the parenthesis will give you a curly brace. That's important anytime you reference a list. And let's put all 3 of these in. 2 and comma 2. Let's go back. 3 and 4. Then second and a closing parenthesis. Okay. And now I paste this in. So there's the command line, what it looks like. Okay. Press enter. And what do you notice? Well, that gave me as a result, so it evaluated the binomial PDF for every number in that list. So the result was a list with all of those probabilities in it. That's pretty darn cool, right? Very awesome. So now, what if we wanted to find the probability of getting 2, 3, or 4 right? Now that we calculated this, what do we still have to do with those probabilities? Yeah, we have to add them up still, right? Well, there's some options here. So first, we could just note them down and add them up individually. Okay. So alternatively, we could use the sum function and just enter that list of numbers in the sum. Okay, so we could do this. So hit your, look, second and stat gives you your list options. All kinds of things we can do with lists. We're going to hit right and go to operations, go down to, oh no, we want to go over to math, sorry, and go down to the sum function. And this will add up everything in the list that we provide to it. So let's say we were just going to do this binomial PDF as part of that sum. So we do the sum, do the binomial PDF with this third option as the list of all of those numbers. Boom, it adds those up. Now, that gets a little bit confusing, okay? So here's my recommendation for what to do. So let's just go to the stat and edit screen. And let's use our lists variables here to our advantage. So clear, boom, let's clear this one out. Okay, so in this first one, let's put in all of the outcomes that I want to be adding up. So 2, 3, and 4. Good. And now in list 2, hit up, and now we're going to enter a binomial PDF formula in the heading of list 2. That's great. So we'll hit second and variables, put in binomial PDF, just like that. Okay. We still have 4 trials. We still have 4 trials. The probability of success is still 0.2. But now let's delete out the X values that we had in there. And now let's put in list 1. So it's going to automatically do this calculation for everything in list 1, and it will populate all of list 2 for us. Now that is awesome. Okay, and so now when I quit out, I could do my sum option. So sorry, second and stat, go to math, sum, and now rather than putting this crazy binomial PDF expression in there, I can just put in, oh, sorry, I want to add up everything in list 2, all of those probabilities. Sum, second and 2, close, boom, much neater. Okay, I really like that method a lot better. That makes sense? All right, now currently in our edit list, we only put in the outcomes that we wanted to add up. If I wanted to have the entire probability distribution in here, I could just by default find all of those probabilities at once. So I would have to increase my list here though. So in list 1, all of my possible outcomes for Eric to guess on this test are what? How many questions could he get right? Well, he could get none of them. So the first option, 0, he could get 1 right, 2 right, 3 right, or 4 right, right? Okay. Well, now, so we may as well calculate the probability for each of those. So hit your up arrow. Let's put in our binomial PDF option into the heading again. Right there, option A. And we're going to leave in the X value spot, list 1. So again, there's your command line TI-83 people. Binomial PDF 4, comma, 0.2, comma, list 1. Press enter. It populates this for the entire binomial probability distribution. That's pretty slick. Now, any probability that I need to generate using this distribution, I can do now with these probabilities. Okay, if I wanted to find the probability that Eric gets no more than 1 right, I add up the 0 and the 1 probabilities, right? If I want to find the probability that Eric gets at least 3 right, now I add up the 3 and 4 probabilities. Does that make sense? So all of the probabilities I need are in this list, even if it's a kind of a compound probability that I'm looking for. That makes sense? So for example, by the way, this table, you're filling in with those probabilities. Nice. Make it happen. Okay. So now we get to do these examples. So what is the probability that Eric gets all 4 questions right? Well, look, it's right there in our probability distribution. And we calculated it before as well, right? 0.0016. It's all done. What's the probability that Eric guesses less than 3 questions right? Well, that means 0, 1, and 2 are our valid options, right? So we write down each of those probabilities, 0.4096 plus 0.4096 plus 0.1536. And that's going to give us a result. That makes sense? And that's manageable. That's not too bad. And then what's for the probability that Eric guesses more than 2 correctly? Well, which outcomes are more than 2? That's 3 and 4. So the probability of 3 right is 0.0256. And the probability of 4 right, so 3 is the first one, 4 is the second one, 0.0016. And we get to find that value, and that'll give us that result. So the moral is, it's going to be beneficial on these types of problems. Just put in the whole probability distribution in your calculator, and that will give you all the probabilities you need to work with. And you can do that addition even by hand, and that's nice and slick. Cool? So using this method with the whole probability distribution is going to be nice, especially when you don't have a large number of trials. Okay? A manageable number of trials, you know, even 8, 9, 10 trials, that's not too bad. But when you end up having a 100 question multiple choice quiz, right? Now it's going to be pretty tedious to put in the entire probability distribution. So in our next lesson, I'll talk about another way to deal with those so it's not quite so tedious. Okay, so for now, for this lesson, this method is going to work just fine. Now as with all probability distributions, right, you can find an average and a standard deviation for these problems. So I gave you in our last lesson formulas for finding the mean and the standard deviation for, in general, any probability distribution. So we can simplify those formulas when we know that we're dealing with a binomial probability distribution. And here's those formulas for you. Okay, the mean, or the expected value, is simply n times p. N times the number of successes that you expect. The standard deviation is the square root of n times p times q. So all numbers that we have, right? So in our problem with Eric, what is my n? My n was 4. P, my probability of success, was 0.2. So what is n times p going to be? Well, that gives me 4 times 0.2. That gives me 0.8 as the mean for my binomial probability distribution. Okay, well, if p is 0.2, that means q was 0.8, right? So I can plug that into our formula for standard deviation and do the square root of 4 times 0.2 times 0.8. Okay, that's not too bad. A lot more convenient than the general version that I gave you in the previous lesson, right? So 4 times 0.2 times 0.8, and you do the square root of that, and you end up with 0.8. That's not, they don't always match, but in this case, they ended up matching. Good? Well, because you took the time to put the entire probability distribution in your calculator, we can also use our one variable stats option with the frequency list of the probabilities to find the mean and standard deviation, just like we did in our previous lesson. Awesome, so hit stat, go to calc, enter on one variable stats. Our first list is going to be list 1. Frequency list, we'll make list 2 because that's where our probabilities were. And we press enter and look. X bar, there's my average. Sigma, 0.8, there's my standard deviation. So your calculator can do this for you too. Even though the formulas for binomial probability distributions are not too bad to find the mean and the standard deviation. Good? Awesome. So have those formulas in your list. You should have in your list or in your notes the binomial PDF function and what it does. So essentially the binomial PDF function finds the probability of your successes being exactly equal to a specific number, right? You'd use binomial PDF with N, P, and R in there, okay? So know that connection. Know we can generate the entire probability distribution in our tables, enter the outcomes into list 1, and then in the heading of list 2, do a binomial PDF, but for the third option, just put list 1 in, and it'll automatically generate all the probabilities for all of the outcomes in list 1. That's going to be a time saver. That's big. All right, now take that knowledge to your groups and go deepen your understanding. All right, I'll be in touch.